Imagine living in this peaceful village where fresh and clean water flows straight to your tap. But the problem is that you have to draw water from this river and clean it before your consumption, because we know how difficult it can be to get water on mountains and hills. So obviously it needs pumping. And one of the unsung heroes of engineering in case of pumping is known as the rising mains. This plays a very important role when water has to be transported from lower elevations to higher ones, overcoming the pull of gravity. These play a very crucial role in ensuring that even the highest homes on the hillside can enjoy the same reliable water supply as those in the valley below. In this lecture, we are going to discuss about the design of rising mains, in which we will discuss some theoretical aspects, and then we will be doing some designs based on Excel and APANET, which will give you further clarity. Now, the calculation of rising main is a domain aspect of mechanical engineering people, because this involves the pumping machinery and power calculations. And therefore, as hydraulic modelers, we do not need to calculate the optimal sizing of rising mains. Okay, but since this is a part of a network, that's why I'm teaching you these things. Even if you don't have to calculate, you should be knowing the related aspects of its design. In this video, I will also be providing a detailed Excel sheet that you can download from the description. And if you put simple values in that Excel, that will give you the optimum size of the rising main pipeline. Now, if we talk about the network, this is how a network looks. Starting from the source, there is a pumping machinery from which the rising main takes the water to the tank. And then it is further distributed through the distribution network. Now, we all know that we design a variety of pipes whenever we are laying a distribution network. So the question is, why do we need to design the rising mains separately? Why can't we just design it along with the other pipes in the distribution network? So there are several reasons for that. The first reason is elevation change. The function of a rising main is specifically designed to transport water from a lower to a higher elevation. Especially, it is most of the times connected with a pump. So this requires significant pumping power to overcome the gravitational and the frictional pulls. Whereas in contrast, most of the distribution network pipes operate under relatively consistent pressure and elevation changes. Okay. So while the elevation changes in a rising mains can increase drastically over a very small length, whereas in distribution lines, the change is not that drastic. Again, if we talk about the calculation of the head, the total head for a rising main includes both the static difference as well as the head loss due to friction. It is needless to say that this critical factor of two components does not apply uniformly to the entire distribution network, and that's why we need to calculate it separately. The other factor is pumping requirements. So there are energy costs associated with pumping water through a rising main, and it depends on the elevation difference, flow rate, and the efficiency of the pump. So accurate calculation of these costs is essential to ensure economic feasibility. Moreover, the pump sizing is very important, and for that the rising main is a crucial component, because undersized pipe may fail to deliver the required flow, while oversized pumps can lead to inefficiency. The third character is hydraulic characteristics. The rising mains need to maintain specific velocity and head loss criteria to ensure efficient operation. These parameters are closely tied to the pipe dia and material, which needs precise calculation. And then when we talk about the pressure management, the pressure at the pumping station and at the discharge points need careful management to avoid issues like cavitation and water hammer, which are less of a concern when we talk about the gravity fed sections of the network. Then again there comes design complexity, because there are different scenarios that rising main often encounter, such as steeper slopes, higher pressure requirements, and this requires specialized design considerations. Then there should be isolation for maintenance. So this will be requiring different valves and control mechanisms compared to the broader network. Then cost implications. The initial and the operational costs, that is the cost of laying and operating a rising main, can be significantly higher due to the need of robust materials. Generally, for designing the rising mains, the material used are cast iron, mild steel, ductile iron, RCC, pre-stressed cement concrete, polyethylene, asbestos, glass reinforced plastic, and bar wrapped steel. Right? So now we are clear why we need to calculate the rising mains separately. So next, now move on to how to calculate the requirements for the rising mains. So the calculation of rising mains involves a series of steps, and the first step is to collect the data. And the data involves the flow rate, that is the amount of water that is to be transported. It can be in liters per second or cubic meters per hour. Then the elevation difference, which is the vertical height the water needs to be lifted, the pipe length, the total length of the rising mains, then the pipe material, that is the roughness coefficient, the energy cost of electricity for pumping, then the cost per meter of pipe for different diameters. Once we have gathered all this data, then the second step is head loss calculations. So the head loss in a pipe can be calculated using the Hazen-Williams formula or the Darcy's-Weisbach equation. We can use any of the two formulas for our calculation. Once we have calculated the head loss, the next step will be the calculation of total head. Now this total head will be the sum of elevation difference plus the head loss due to friction, right? Then comes the step number 4, that is determining the pumping power. Now again, as I have told, that this is an aspect of mechanical engineering calculations. So you don't need to worry that much about this, but just know this step. Once we have calculated the pumping power, then we move on to calculation of the energy costs. The annual energy costs, which can be calculated by multiplying the power with the operational hours and the cost per kilowatt hour. Once we have done these steps, then we can make an Excel sheet and we can compare different pipe sizes by taking into account the velocity, the head loss, the energy cost, and the pipe cost. You don't have to do all these things, firstly, because you are not related to the mechanical aspect of water distribution design. Secondly, even if you have to do this, I will give you an Excel, and that will make the process much smoother and easier. Now that we have learned the underlying concepts of design of rising mains, let's move on to creating a small rising main network, firstly in EPANET, and then we will create a detailed network in Excel. So let's start building a small rising main network for EPANET. Till now we have completed more than 45 to 50 lectures. You can get a list of all those lectures from the playlist section, and then you can go to this complete design, and here you can see that so many lectures are there. We have already discussed so many designs in these entire lectures, and this design of rising main is in the continuation of all those lectures. You can also get detailed views about how to use EPANET and its various functionalities. However, I will still try to repeat everything in this video. So this is the interface of EPANET. I have already drawn a reservoir for you. So the case is very simple. There is a reservoir, or you can say an underground aquifer, from which water has to be pumped out, and it has to reach at an elevation which is 250 meters higher than the elevation of the reservoir itself, right? So first we have drawn a reservoir. Now we draw few junctions or nodes. Now we connect these junctions with a pipeline. Once we have connected the junctions with the pipeline, we now move on to creating a pump from the reservoir to the first node. Now we have created a pump, and there is an additional pipeline between the reservoir and the node. We delete that. This is how we create pumps in EPANET. Now we try to put the various data for various pipelines and junctions. So first we put the data for the reservoir. The total head here is 10 meters. And then this is at the same elevation as the reservoir. So 10 meters again. And then the third node where the water has to be taken to, this is at an elevation of 260 meters, which is a difference of 250, and the base demand is 1 million liters per day. Then the pipeline, the diameter initially we consider 100, and then the length is 500 meters. So you can see that in 500 meters we are covering a height of approximately 250 meters. So it clearly means that it is a kind of hilly terrain or something. So we are done with most of the things. Now we go to pipe definition, and for that we can go to the right side and select curves. Now the curve ID we leave as 1 only, and the initial iteration we consider the flow as 1 MLD and the head as 250. Okay, this is the process of how we go for the design of pumps. You can see these videos for more details on how to design pumping systems. So flow is 1 million liters per day, and then the head is 250. We change the default units because it's not in million liters per day. Right. Now we assign the pump number 1. That is the curve we just designed to this pump. Then we run this network, and it is saying that some negative pressures have been found. So to check where the negative pressures have been found, we right click on any empty space in this network, and then we try to visualize that data. So you right click and select options, and then go to notations and check these two boxes. And then on the right side panel we can go to pressure on nodes and then flow on links. Right, so what do we understand by this? The flow through the pipeline is 1 million liters per day, so that is not an issue. but the pressure is negative, which means the water is not reaching the topmost point. The pressure at the first node is 250 meters. So it means we are short of approximately 12.5 meters of head of pressure. So if we increase the capacity of our pump for a flow of 1 million liters per day by a magnitude of more than 12.5 meters, the water will start reaching there, right? Again, you cannot design a pumps based on your whims and fancies. These pump curves that we are designing has to be provided by the pump manufacturer. But just to understand these processes, I am explaining you with a simplified version. In this design, again, we are not going to see the cost related aspects because there can be multi-dimensional analysis in softwares also. So in the next example, when we see a detailed Excel, we will see the cost related aspects also. Here our discussion is mainly related to the hydraulic aspect, rising mains, right? So we try to change the pump definition and we increase the head so that water can reach to the elevation that we need it to reach. And for that we change the pump definition. So from 250 we make it to 280. And then we hit OK. And then we run the model again. So now it is saying that the run is successful and we have a residual head of 17.5 meters at the topmost level. So it means hydraulically the network is good. But again, few more aspects are remaining. That is the velocity in the networks and the head loss per unit length. Now this is a criteria for the distribution networks, but we check here for rising mains also. This is not necessary because rising mains design is altogether different, but still to give you clarity on how to change such things in your distribution network, let me explain this also here. So the criteria for velocity is that the velocity should be in a range of 0.6 to 1.6 meters per second. And the unit head loss should be less than 10 meters per 1 kilometer of pipe length. First we check the velocity criteria. For that we select in the right browser velocity in the links section, and then we change the color coding, and then we see that the velocity is 1.47, which is in the range, right? So we don't need to change the velocity. Now we move on to unit head loss, and here we see that the unit head loss is 24.98, which is much higher than our limit of 10. So we try to reduce it, and to do that we can increase the pipe dia, because simply saying the head loss here is more, it means the water is hitting the pipe's internal wall aggressively. So if we increase the pipe dia a bit, that friction can reduce. So we increase the pipe dia from our initial assumption of 100 to 150 now, and see if it makes a difference. Now we run the model again, and then we see that the head loss per unit length has reduced to 3.47, which is very good. Now we cannot put pipe sizes with a random value in the design because it has to match with the pipe sizes that are available in your market. But since we are doing it here for understanding purpose, we can do such modulations to get a better grasp over the concepts. But remember this, the pump definitions and the pipe sizes will be taken from the standard readily available material that is available in the market, right? Again, since we have increased the pipe dia the unit head loss is okay, but let's check whether there is a change in the velocity and if that change is within the permissible limits. Right, so velocity here has decreased, which was anticipated also. However, this velocity is in the range suggested by the codes, that is from 0.6 meter per second to 1.6 meter per second, which means with the point of view of hydraulic design, this model for the design of rising mains is okay. Now we move on to a more complex design, which we will be doing in Excel. Now this is an Excel sheet which you can get from the link in the description below. However, it can only be unlocked by the people who have been our members and constantly supporting us, and to become a member you can check the link in the description below. So if you get this Excel only, 99% of your problems related to this design of rising mains is going to get solved. However, I am just giving a little bit of introduction on how to use it. Again, this is more in the domain of mechanical engineers, so you don't need to focus much on this. But since rising main is going to be a part of our design, that's why we are discussing a little bit about it. Okay, so in this we put the water requirements for various periods. You can also change the years and then see whether any additional modifications are needed with respect to those changed year in further columns. Then we need to put the length of the rising mains that we have calculated from the distribution network, the static head, the design period, the combined efficiency of the pump that has been provided by the pump manufacturers, then the cost of the pumping unit, the interest rates, and then the life of the electric motor and pump set. Right? Once we input that data, then we will see the other steps that are there in this design. So we do that. So I'm just putting design data from a design which I had done few days back for a company. So this is the data for rising mains. You can use your own data. You are very free to do that. You can also put the data of your existing designs which you have done earlier. And trust me, this will give very accurate results. So just to explain the perspective of the data, we have put the data and then we can see that the pipe diameter in millimeters for various pipelines have been given here. Then the material under consideration is mild steel. The Hazen-Williams constant for mild steel is 140, and then the rates of various pipe diameters has been given in the column next to that. Then the design has been bifurcated in a duration of 15 years duration each, and then the average flow for these 2 different years have been calculated. You can click on each of the cell and see the corresponding formulas from which it has derived to get the better understanding. For example, here the average discharge is 2 mld, which is corresponding to the formula bar F18. So F18 is the design at the end of the discharge at the end of 15 years, 2 mld. It means here the average discharge that we are considering is the maximum of the 2. Similarly, in this also 3 has been taken, right? And based on the hours of pumping that you need, you can change it here for your convenience. And the modified Hazen-Williams formula for velocity and head loss has been given. Now for various lengths and diameters of pipes, length is same everywhere. and for the various diameters of the pipe, the head loss has been calculated, and correspondingly again the velocities have been calculated. Similarly, this has been done for the second duration of 15 years, and this is a table which contains the cumulative head losses, including the static as well as the friction head loss. Okay, you don't have to do any of these things. You can just put your data in this Excel and it will do everything automatically. Then there is a comparison on the cost related aspects of various diameters of pipe. Again, this is the comparative statement and the final table for the overall comparison for the design of pumping mains. So here you can see in this last column that there are various costs associated with various kinds of diameters of pipes. So in this table we can see that the cost associated with a pipe dia of 150 is the least one, that is 27,696. So this will be our optimum size for the rising mains, right? These minimum values will be calculated automatically in this cell here. You don't need to worry about that. And if the associated costs and the per unit costs is different in your country or your area, you can change anything in this Excel. I am providing it to you. You are free to do any modifications for your understanding purpose and also for your design purpose. So I hope you got some clarity on design of rising mains. If you need to download this Excel sheet and watch the full course, you can check the links in the description. The password is RISING without space MAINS, this in the same order written here. Thanks for watching. Have a nice day.